Okay, class, in this lecture we're going to cover just some of the basics of jet propulsion, jet engines, starting with the history, a little bit in the history. There were really two individuals working on this throughout the 30s. One was a Brit, Frank Whittle, and the other was a German, von Ohain. And I believe that they weren't aware of each other's work. Frank's original work came out of his senior thesis, which I thought is interesting, a senior undergraduate thesis at the RAF Technical College, but really the Germans during the war were the first to put these on jets, World War II. The most prominent plane being probably this Messerschmitt 262 that came online towards the end of World War II. And the Germans were short on fuel, but it was highly effective against the Allied aircraft. And this was really the beginning of jet propulsion, still subsonic, but jet propulsion leading to these higher performance vehicles. Just as some background on the jet cycle itself, the cycle we refer to as a Brayton cycle. These are air-breathing jet engines, and you effectively can divide it into these four pieces as shown at the bottom here. So there's analogous to a four-stroke engine, closed cycle engine, but here we have the intake. This mimics the intake, the compression portion here. Combustion is the third component, and then the exhaust. So you can see the analogs with a four-stroke internal combustion engine shown here. Now, the actual PV cycles or thermodynamic cycles are different between the Brayton and Otto cycle. Here's a typical four-stroke Otto cycle where you have expansion of the cylinder, compression, ignition, and combustion. The work being done as the piston is pushed down. In this idealized sense, we release the heat in this constant volume process, and then we exhaust the air back to the exhaust manifold and start again. So this is obviously idealized. It's always presented this idealized case where, for example, combustion occurs at constant volume as this heat release here. A real engine cycle this doesn't occur. Combustion occurs over some time frame, but this is the way it's idealized. In the case of a Brayton cycle, you have a pretty similar closed loop here. You have the compression here, mimicking stage 2 to 3 in the prior diagram. Then the combustion here, where you have the heat energy added, is not occurring at constant volume. You can see here that the volume is changing, it's expanding. The actual expansion, the useful work being done through the turbine and the nozzle. And since it's just not the same air molecule that arrives at the beginning again, we have this exhaustion back to the ambient air pressure right here. The key for both engines in terms of efficiency is this pressure ratio, or compression ratio as we refer to it in internal combustion engines. The pressure ratio is important. It basically is the amount of work we can do, we can get out of the fluid is based on how much we pressurize it initially. The fundamental thrust equation, we'll just go through it in sort of a cursory analysis. I did put in the appendix of the lecture notes. This is also in Anderson's book, The Full Derivation, Momentum and Mass, where he considers this as a control volume, a closed control volume, where you have a solid wall along the actual engine itself. And here we're considering thrust from two contributions. One is change in momentum, and the other is pressure, the actual pressure force acting on that control volume. So starting from the pressure force, you have the exit pressure times the exit area acting on this direction here. So that actually is a thrust force. So that's why P's on the positive side here. A drag force from pressure on this side, pushing backwards. That's P infinity, or free stream pressure. So you have this pressure difference acting across this control volume that actually can contribute to this x direction force, or thrust drag force. We also have a change of momentum. So exiting the aft end of this engine, we have mass flux times the velocity, and that mass flux includes both the fuel contribution, which gets injected in at some point here, and the original air contribution that's traveled through the entire engine times the exhaust velocity here. That is the momentum leaving the engine here, and in the intake here, you have a momentum contribution, which is simply the mass flux of the air that passes through the engine times the free stream speed, or speed the engine is traveling through the air. This ratio of mass fluxes of fuel to air we call F. And typically, this is actually probably a little high, but it's small. It's in the low percents, the ratio of fuel to air, and this is really the mixture that's like in a car. You're trying to mix fuel and air in the right quantities from the stoichiometric quantities to try to get as complete a combustion as possible. As similar things are being done in these jet engines. So we have a fairly low value for F, and if we come back to this equation here, and we simplify it by, if we assume simply that F is small, so this essentially the fuel mass flux, this term right here is not important, and we have a minimal pressure difference across, so that the exhaust pressure is close to P infinity, the exit pressure is close to P infinity, then we can get rid of this term here, and we're left with simply this m dot air times VE minus this m dot air times V infinity here, and we can write our thrust equation. This simplified thrust equation here, again, it assumes a low fraction, pressures are equalized. This is the same exact equation as we saw the propeller. For the propeller, that there was this velocity difference times the mass flux passing through it, and it was giving rise to the thrust. In terms of efficiency, we can write it in this expression this manner. So we have this theoretical efficiency of 2 over 1 plus this velocity ratio. And so if we want the efficiency to be as high as possible, then we want that exhaust velocity to be as close as possible to V infinity. This is the same case that we saw with the propeller, although the expression isn't quite the same, but this idea that we don't want a large velocity rise, there we wanted a low induction factor, here we want a low velocity ratio. So small changes in velocity are important for high efficiency, but also we need changes in velocity to produce thrust. So thrust again has these two components, just as it did in the propeller case. A change in velocity and this mass flux component, which includes basically how much air is passing through the engine, or in the case of propeller, through the propeller disc. And so we want this one to be small, if possible, if we want it to be efficient. So small for high eta, which means we're going to need a lot of this in order to have the T that we need. So this is, again, still analogous to the idea of the propeller, that we don't want to take all our gasoline energy and convert it simply into kinetic energy of the air. That isn't useful to us. So what we would like to have is thrust without a large change in velocity. So really what jet engines do for the most part is they produce this high change in velocity. So they are typically, they're in the families of jets that we'll look at. They tend to be a lower efficiency. A turbojet tends to be a lower efficiency. Props, because they tend to use large blades, have a smaller associated velocity increase. The problem with props is that they're only good up to about 450 miles per hour for a typical prop plane, because at that point the tips start to suffer from high Mach number effects. You start getting supercritical flow at the tips, and that causes noise and other factors that are to be avoided. So the solution that the aviation industry came up with to get efficiency and also be able to have it function at transonic and supersonic speeds is a turbofan. It's really kind of, you can think of it kind of like combining the two. You get efficiency that's closer to a prop, but it still produces good thrust at these higher Mach numbers. And it looks something like this. And so there's actually a duct around the fan here. So we add this sort of fan to the front of the turbojet engine. We still have the turbines themselves, which are back here where the flow is expanding. Those are turning a shaft. In this case, you end up with multiple shafts. It's a little hard to see this diagram, but here it looks at least like they're trying to draw two concentric shafts. A green one here that's being driven by the low pressure turbine, the later stage turbine here. This low pressure turbine is right here, driving this green shaft here, which is spinning the low pressure compressor stage here and the fan at the same time. And they have these purple stage of the turbine, which is the high pressure part, driving the high pressure portion of the compressor here. So it's actually concentric shafts, and you can imagine how mechanically complex that is to have these concentric shafts that really can never fail, spinning rapidly for multiple, a significant portion of each day. So we have this fan now. So there's divided flow. Some flow actually passes through the engine. Some air passes through the fan itself. So you can think of this like a propeller essentially added on the front here, but it's a ducted propeller in order to get the flow to slow down. So we don't need these large velocity jobs to get the thrust that we need. And so this is a way of sort of combining those two ideas, a propeller and a turbojet. It's a way. We'll look at a different way at the end of the lecture. And this is much more common. And this fan is what you see when you board an airplane. You look down. You're looking at the fan on the front of the airplane. And so these lead to higher efficiencies, and we can quantify the flow through here in much the same way we did with the turbojet, but now we have to consider the fact that some of the mass passes through the fan and not through the engine itself. So we'll look at some definitions. So that m dot through the fan is this new variable. We still have the m dot of the fuel and of what we now call the core flow, which is what's passing through the jet and actually being combusted. So we have this still have remaining ratio m dot fuel to m dot core. That's the same F as we saw before for the turbojet, but we have a new ratio, which is the bypass ratio, which is the ratio of mass flux that passes through the fan on the outside of the engine itself, but through the fan, and to the flow through the core. Now, jet fighters have a very low bypass ratio, and we'll see why in a few diagrams. Modern commercial aircraft, commercial transonic aircraft, like you would fly to on a vacation on, have much higher bypass ratios, typically 6 to 9. I think we'll look at the G90 engine later. It's a bypass, I think, of 8. These engines that are on the 737 MAX that cause Boeing to make these odd design changes, which we're dealing with in the news now, those engines have bypass ratios of 9. They're very efficient, and we'll see that the bypass ratios increase through time. We have, if we consider this control volume as this dashed box, we have to consider the exit velocity from the flow through the fan, the exit velocity for the flow through the core, as being potentially different. And of course, the flow that went through the core had heat added to it. It's been combusted. There's fuel mixed in there. Now it's very different. So this would truly be a slip line here, separating very much two parcels of fluid that started the same, and it had very different fates. And again, if we consider F around 0.05, then we can begin to do a similar control volume analysis, where here the momentum out has to consider the core flow, the core velocity, times the mass flux of the core, plus the mass flux of the fuel that was added to that core flow. So this is the same as before in the turbojet. We had to consider those two components passing through the exit or exhaust of the engine. But we also have this additional mass or momentum out the back of the fan. And so this is UE, the exit or exhaust velocity of the fan, times the mass flux that passed through the fan. We can simplify this expression by including our our combustion fraction. So this was m dot of the fuel divided by m dot core. We find this on the previous page. And lambda, again, was the m dot of the fan divided by the m dot of the core. That's our bypass ratio. Using that definition, we can simplify the exit portion of the momentum with this expression here. The inlet portion, we have the velocity at the inlet times the mass flux passing through the core plus the mass flux passing through the fan, and we can rewrite this expression using the bypass ratio lambda to simplify that as well. So thrust, again, is this change in momentum and plus the pressure contribution, exactly as we had before. For the turbojet engine, the difference in pressures acting on the front and rear of this control volume times the area of the control volume, AE. And we put these pieces together to get the total thrust, and it leads to this expression right here. And you can see here, if you let the bypass ratio go to 0, this recovers the exact expression we have the turbojet before. Essentially, you have no air bypassing the core. Everything goes to the core and it'll return to the turbojet expression we had a few slides back. We make these same assumptions again, that the exit and inlet pressures are very similar, and that this fraction of fuel, mass fraction, is small compared to the core mass flux, and so, which is reasonable. And we can simplify this expression to look something like this. And this is what, when you go to do your homework, you're going to be plugging in these numbers that you'll have for a given engine to try to come up with the thrust of that engine. So this is the thrust equation with some simplifications, but the thrust equation for a turbofan engine, where you see the importance of lambda in this expression. We see lambda, or the bypass ratio, arriving this expression. We can also use the expansion of the flow through the turbine, which turns the shaft to turn a prop, which has no ducted, essentially it's an unducted fan, a propeller. And we can think of this as a super high bypass turbofan. These are very efficient. It's an efficient way to have subsonic aircraft. So this doesn't work for transonic. If you're talking high subsonic speeds, this is primarily used for commuter type craft, where you are spending a lot of your time taking off and landing, and it's not as critical to get the extra 50 meters per second at altitude. And so we see these on these kind of small aircraft when you go to the airport for regional flights, and they tend to be the most efficient of the engines. But they have this limitation because once these tips up here start to go transonic, then you have issues with drag and noise that is difficult to overcome. In terms of engine efficiency, we can think of the TSFC, or the thrust specific fuel consumption. It's a pretty odd metric. It's pounds of fuel per pound of thrust per hour. That's what you're seeing right there. Pound of fuel per pound of thrust per hour. There's a metric version of this. Oh, yeah, I did write it down here. Milligrams fuel per newton of thrust per second. You see it down there in the corner. Sometimes written this way. So it's not a non-dimensional variable. It's a very dimensionalized variable. Would have the units of 1 per hour. But this does work out to be order 1, which is the nice thing about it. And you can see how, as the bypass ratio increases from 0, or a true turbojet, up to these high bypass ratios of modern turbofans. We talked about, well, this diagram sort of precedes the GE90 engine, but that's getting into the 8s and 9s. And then there's a couple of, and we have turboprops we talked about here, which effectively have bypass ratios over 50. And there's some sort of, there were some attempts to make some alternatives, and I'll just talk very briefly about that at the end of the lecture, and what they call unducted. That UDF is an unducted fan, or prop fan, I think they're also called as well. But you can see as this bypass ratio goes up through these types of engines, for low bypass ratio, which you would have seen on fighters or on early commercial aircraft like a Boeing 707 when it first was released. And over time, on the commercial aircraft, they increased this bypass ratio. And you can see as they did, it lowered, this is sort of a history, a journey through these engines, how it had lowered the specific fuel consumption. That's a higher efficiency engine, less fuel burn per pound of thrust as we passed across these engines. And again, these are the blades you see there are the fanned in that engine. And you can see how it lives within this duct right here. In terms of efficiencies, there's two efficiencies we deal with. A propulsive efficiency, which is what we looked at with the propeller. Basically, we consider the shaft coming out of the engine itself was produced a certain amount of power, and how much of that power went to useful power, which was the thrust of the prop itself times the speed at which you were traveling. So it's kind of useful work over this mechanical work input, so the shaft that's coming into it. And this is what we were kind of seeing, that props are sort of capable of this 70%, 80% efficiency. This is an example of a turboprop curve here. And this shows airspeed. And as you go to higher airspeed, you can see how the turboprop becomes a lot less efficient very quickly. And this is when you get into these high Mach number effects on the blade tips. And you're left with these other options here of different bypass ratios, the higher bypass ratio producing the higher efficiency. And compared to the lower bypass ratio, but these again stop functioning properly at these very high Mach numbers, and you go back to the pure turbojet. This is what you see fighters adorned with today, these very low bypass or no bypass ratio engines on supersonic aircraft. We also have overall efficiency. This includes the efficiency of combustion. So this is basically chemical bonds to useful work. And you think of a car engine as being roughly 30% efficient, internal combustion engine, at least roughly 30% taking the chemical energy that's available in the gasoline and converting it to useful work along the road. We see similar kind of numbers in the aircrafts. So we have this includes these turboprops and the turbojets and low bypass. We see a similar kind of diagram. We've shifted it down. We basically cut it down by a factor of 2 or a bit more, about 2.5. And this comes down to the fact that we're generating a lot of heat that isn't doing useful work, just as we are in the internal combustion engine. This does give a little kudos to this idea of the inducted fan concept. Really, this is 1990s. It sort of started in the 1980s. That we'll look at in one of the last slides. But so what we're seeing is sort of typical in our high bypass. This diagram is from Chevel's book, which is at least the version I have is a little dated at this point. But you're talking about efficiencies from chemical to useful work of about 35%, which would be a good car engine, would be an Atkinson cycle in a car engine, something like that. What has allowed the efficiency to change over time is really materials is a key factor. And so you have this pressure ratio. The compression comes from the compressors, and the total pressure ratio comes from the pressure rise to the compressors plus pressure rise in the combustion chamber. And we see that over time, from the 60s, when they were building these engines, first building these engines for commercial air applications, you had a total pressure rise of about 15, and now with this GE90 engine, which we'll look at a snapshot of, you're looking at something like 40. And this has given rise to much higher efficiencies, but with higher pressure rise comes higher temperatures. And so along to withstand these temperatures and the loads on these things, they had to come up with new materials that can handle the temperatures and the forces acting on them. Composites, big. Ceramics, big. And so these kind of developments really drove the materials industry, particularly jet engines themselves, because they withstand this pressure and heat for long periods of time and with limited tolerance to failure. And you see the same thing. The engine availability date from the 40s to the 90s. this increase in the temperature threshold of the materials that was being used in them, not doubling, but increasing by a factor of about 50%, which is impressive, which allowed them to get to these higher pressure ratios. This shows an example of the G90 engine. This was built, I think, or at least is on the Boeing 777. I don't know offhand if it's used on any other aircraft. And you see that how absolutely incredibly complex these things are. There are, in this, I believe, let's see if it says here, three concentric shafts. So we looked earlier at a diagram that had two, at least to my eye, obviously two. But here you would have, for example, this turbine driving a late stage compressor, and these turbines sections driving an early stage compressor, and maybe these turbine sections driving the fan out here. So you have three concentric shafts, all spinning at different RPM, one inside the other, which already is getting incredibly complex. You have to deal with the bearings for that, both thrust and the bearings that hold them in place. You have your normal sort of sequence through the fan, through the low pressure compression stage, through the high pressure compression stage, into the combustion chambers, which are sort of shown here, but not too well, where the fluid actually gets combusted, into the high pressure turbine stages, into the low pressure turbine stages, and then out the exit. And of course you have your fan here with these beautiful composite blades through which the air flows through this duct on the outside of the core. And so the bypass ratio on this is 8, so this is a little less than the engines we're seeing now, built in the 2000 teens. This is probably dates to the late 90s is my guess, although I don't know that for certain. I did not write that down. We'll say late 90s. A 9-ton engine. The thrust to weight ratio is capable of about 6. Pressure ratio we saw in the previous diagram about 40. The compressor itself, so this is just before it hits the combustion section, the fluid's been compressed by a factor of 20, which is absolutely incredible. And takeoff is basically full on. Each of these engines is blowing through a gallon per second. And at cruise, it's about a third of a gallon per second per engine. On a 777 has 2 engines running a third of a gallon per second, so it's 2/3 of a gallon per second. But if you're going 220 meters per second, this works out to about a fifth of a mile per gallon, something like that. But if you have 300 passengers, now you're talking about 70 passenger miles per gallon, if I'm doing my math in my head correctly. So something like that's the number we've kind of looked at early on in class as being a pretty efficient commercial aircraft. It's assuming you have a pretty full flight, but you're getting about 70 passenger miles per gallon, which is the way it's rated in transport industry, trains and planes and such. So that's quite efficient. I don't know how much we can really improve on that. So this seems like we're really blowing through gas, but because you're flying 220 meters per second plus, it actually is quite efficient in terms of passenger miles per gallon. 20 million a pop for these engines, and you can just absolutely see, all these stages, and each of these stages has, up to 100 of these blade elements here that are, simply not allowed to fail, or you hope that they don't fail. They do all kinds of tests on these. Yeah, I wrote here, they throw frozen birds at them. They shoot frozen birds at them. Make sure that if it could survive a bird strike, or if a bird strike hit, that at least if if a fan blade came off, that it would stay within the shroud and not tear through the side of the aircraft. So absolutely, the complexities is just monumental. When you get to higher speed, these things stop functioning, and you can take advantage of that. You can take advantage of in supersonic flight of the fact that this business right here, which is driven by this business back here, is no longer needed because you can compress using shock waves. And that's the idea behind a ramjet engine, is that you have, if you look at the front of the SR-71, when we looked at that in class, you can see this thing sticking out of it. And the job of that thing, once you're supersonic, is to set up shock waves at the inlet here, which reflect back and forth. And so the fluid, as it passes through here and it necessarily turns around this, forms this oblique shock, an axisymmetric oblique shock, and a compression occurs. Now, in the case of relatively lower Mach number but supersonic flight, so somewhere around Mach 3, 1 to 3, you can slow the flow down enough so that you can you have a throat here. So you see this is a converging nozzle, so it's supersonic here, and it's subsonic here. So the flow goes through this converging section is supersonic flow, which means it's slowing down, passes through a throat. Now it is subsonic, and the combustion can be performed on the subsonic fluid because it's tricky to make fluid combust if it's moving too rapidly. And so these engines take advantage of the ability to compress the shock waves, so of having the compression rise you need using shock waves, but subsonic flow in the actual combustion chamber, and producing this net thrust without any moving parts at all. As you get to higher and higher speeds, it becomes necessary to use supersonic combustion ramjet engines. So this stands for supersonic. The C is combustion, and then ramjet engine. So this would be for a hypersonic vehicle or a hypersonic missile. Would use this. You don't see the throat, so we're not slowing the flow down. We're not basically throttling the flow back to subsonic. We have the same beautiful oblique shock here set up. Compression occurs to that shock, but it's slowed. The flow is slowed and compressed, but not to subsonic Mach number. And so the combustion occurs at supersonic speeds and then is expanded back out. So obviously these engines are beautiful. The problem with them, of course, is they do not function at all at subsonic speeds. You can't take off with these engines. And so the engines we see, like in the SR-71, are a mix of these and a turbojet engine, where you might have some ability to manipulate the geometry of this thing to make it useful when you need it to be useful and not really present when, or not really affecting things when you don't want it to be. And if you are interested in those kind of, how we build these kind of ramjet, actually SR-70 was a ramjet engine, how we build these ramjet engines, make them useful. I forget what the SR-71 engine is. It's something like a J86. I'm sure it's on Wikipedia, but they would probably have a picture better than I can explain of how that engine functioned both during takeoff when you need maximum thrust at subsonic velocity, so you need actual compression from compressors, and then later when it's actually functioning and flying at Mach 3 plus, how it's able to produce thrust. The Concorde is another example of that, a jet engine that was flying supercruise at Mach 2 plus for hours on end, but also had to take off and produce maximum thrust at takeoff. And there they have these ducts. These are the intake ducts of the engines itself under each wing. And they were able to manipulate the geometry of these intake ducts to allow them to create the shock waves when needed. There was also a little hatch here down here, which isn't really shown, but they could open this hatch. I think it went up at takeoff, if I remember correctly. It opens and closes like that. And so when they need to increase the core flow to the engine at takeoff for maximum thrust, they could open this duct up right here. And it wasn't particularly efficient engine. At cruise, you're talking about 1.2 TSFC. So this is the high end of the chart we looked at before. I don't recall what the passenger miles per gallon of the Concorde is. It's in the teens, I believe, something like 15 passenger miles per gallon. But people who flew this weren't afraid of throwing their money at the fuel that was necessarily carrying them across the Atlantic. But these engines were specifically made for this vehicle, only made for this vehicle, and they are radically complex because you already have a turbojet engine, but you have all this kind of monkey business in front to be able to manipulate the geometry as you transition from takeoff, max thrust, subsonic, to supersonic cruise or supercruise. Sometimes you hear about afterburners, or sometimes referred to as reheat. And essentially, this is a way of getting additional thrust as a temporary measure. And so this is usually discussed in terms of military aircraft or jet aircraft. And essentially, you have a section of the engine, an afterburner duct here, in which you inject additional fuel that you burn. And that heat increases the exhaust velocity, and so you get additional thrust from that velocity jump. They are not efficient. You can see here, just a rule of thumb, you go from a turbojet with a TSFC around a 1, and again, this is a specific fuel consumption, thrust-specific fuel consumption, which we want to be a low number, and it bumps up about 50% when you turn on the reheat, the afterburners. So you can burn through a lot of fuel, but this is typically used in military aircraft to get them above where they might cruise at low supersonic or even subsonic speeds to higher supersonic as a temporary measure. Gives them that additional thrust which they need, which is useful in certain mission criteria. Gas turbines are used for other vehicles, not just airplanes. In that case, you have these very similar kind of looking turbojet driving a shaft. So this shaft might do useful work. In the case of a prop fan, it drives the prop. In the case of a turbofan, it drives the fan. In the case of helicopters, as shown here, you have a turbojet attached to the shaft. It goes to a gearbox, and it goes up and drives the blades. And in tanks, like an Abrams tank has a turbojet, and that drives the tracks themselves. It provides powers for the tracks themselves. Hovercraft here, engine here, and so there are many other applications of turbojets. Also been used in some cars to try to break world record of car speeds. You see them used in hydroplane racing or sort of unlimited class hydroplanes. So they find their way into other worlds. I think there's also some people working on jet engines for those wingsuits, I believe. Don't they have? There's some Swiss guy who's working on these mini jet engines attached to your body and propel you in those wingsuits, or with a stiff wing that you attach to your back. Anyway, there was in the air in the 80s, which was really, I think, caused by a rise in fuel prices in the early 80s, late 70s, gave this sort of incentive to get a big jump in fuel efficiency. And there were two companies, GE and the other, I think, was Allison engines, were working on some sort of concepts at the time of essentially getting to higher bypass ratios, making a big jump in bypass ratio. And one of these is this inducted fan. You can think of it a little bit like a turboprop. And here they refer to it as prop fan. GE called theirs an UDF or inducted fan. And you can see this looks similar to a turbojet where you have a compression stage here. You have your combustion stage here. You have your turbines here. Turbines only driving the compressors. So far it's basically a turbojet. But then you have these hot gases here passing through the second section here, and these fans here are used extract energy from that flow to drive these external props. And one advantage of that is it was direct drive. There's no gearbox, at least in the GE design. I believe the Allison design, I'm not sure, but there's no gearbox between these fan units and internally and these external ones. And so you essentially got a very high bypass ratio plane engine without a gearbox, and the expense of a gearbox, complexity, and maybe most importantly weight. And they had these beautiful unducted blades. You can see these are swept back, and so they operate better at a high Mach number. And this concept was explored quite a bit, I believe, through the 80s, but never really took off because it was expensive to really change engine technology. I did put a link in the PDF to a nice history of this project. So I'm going to end there. The lecture notes have Anderson's analysis, if you want to look at it, of the thrust equation for engines using true control an actual control volume theory with momentum and continuity equations. And otherwise, that's all I wanted to say.